Imagine this scenario. You have just spent, maybe 3 days writing what you believe is the perfect, elegant Terraform configuration.
Oh yeah, we've all been there. It's
Yeah.
a great feeling until you hit enter.
Right. You are tasked with provisioning an entire SAP business technology platform estate. You have your subaccount definitions, your entitlement mappings, and your Cloud Foundry environment instance, all beautifully codified.
Sounds incredibly satisfying.
It does. You sit back, take a sip of coffee, and type Terraform apply into your terminal. You expect to watch this monolithic magic unfold. But instead of a provisioning sequence, the terminal just immediately spits out a fatal dependency error.
The dreaded red text.
Exactly. Your
Uh-oh.
monolithic dream is just dead on arrival. And why? Because the Terraform engine, it simply does not care about your intended infrastructure sequence when it comes to provider configurations.
Yeah, that error screen is basically a rite of passage for platform engineers moving into SAP BTP.
It really is.
We are looking at a fundamental architectural conflict here. You're trying to use a single Terraform execution state to provision a BTP environment and then, immediately bootstrap a Cloud Foundry space inside that environment.
Which seems completely logical.
Logically, sure. But the mechanical reason it fails is because Terraform requires all provider configurations to be fully resolved before it even attempts to read your resource blocks.
So, welcome to a highly technical, granular deep dive into advanced Terraform configurations for SAP BTP.
Let's get into it.
If you are an enterprise architect, a platform engineer, or really just a developer trying to wrap your head around multi-provider setups, we are going to dismantle this exact problem today.
Piece by piece.
Right. Today, we are mastering the multi-provider setup for Cloud Foundry, and then we are going to operationalize the infrastructure handover via a CI/CD pipeline. I will be framing the structural logic, the dependency graphs, and the architectural whys of our system.
And I'll be driving the execution. We're going to go step by step through the exact configuration paths, the directory structures, the .tf files, and the precise CLI syntax you need to bypass these limitations.
Because we're treating infrastructure entirely as code.
Exactly. Which means getting our hands dirty with state refactoring, data source construction, and automated self-service via issue ops.
So let us deconstruct that initial failure state, what we call the multi-provider dilemma. When you architect a BTP environment, the natural inclination is to build a single source of truth.
Yeah, you want it all in one place.
Right. The logical architecture suggests a seamless flow. You spin up the BTP subaccount, you assign the SAP HANA cloud entitlements, you create the Cloud Foundry environment.
All in the same run.
Exactly. And then in that very same run, you configure the Cloud Foundry spaces, the orgs, and the user role collections. It feels like it should just be one overarching directory.
The intention is sound. You have the Terraform provider BTP handling the subaccount layer, and you want to pull in the Terraform provider Cloud Foundry to handle the operational layer.
Because HashiCorp's registry makes it trivial to declare multiple providers in your provider.tf file, right?
It does. It's super easy to declare them, but the execution caveat hits you during the very first phase of the Terraform lifecycle.
I want to build a mental model of that lifecycle because my instinct as an architect is to just lean on native dependencies.
Which works for resources, but not providers.
Right. Let's unpack that. If I am writing standard Terraform and resource B requires an output from resource A, Terraform's directed the acyclic graph. The DAG handles that automatically.
Beautifully, yes.
Or, if I want to be explicit, I just add a dependent block to force resource B to wait. So if I map that logic to our BTP problem, why can't I just put a dependent block inside the Cloud Foundry provider configuration?
Just force it to wait for the BTP provider to finish building the environment.
Exactly. Why doesn't that work?
Well, that approach won't even compile. It fundamentally misunderstands the difference between a resource dependency and a provider initialization.
Okay, break that down for me.
The DAG is indeed a graph theory concept. Resources are vertices, dependencies are edges, ensuring everything builds in the correct mathematical sequence. But the DAG only applies to resources and data sources.
Not the provider itself.
Right. The provider is the engine itself. Think of the Terraform engine as a municipal building inspector.
Oh, I like this analogy.
The inspector demands to see an active functioning electrical grid, which in our case is the Cloud Foundry API URL, before they will even look at the blueprints for your appliances.
Wow.
If that API endpoint does not exist yet, the inspector just tears up your permit.
So the provider configuration phase happens before the DAG even attempts to map the resources.
Precisely. When you run Terraform init and Terraform plan, Terraform evaluates provider configurations strictly during the initialization phase, long before any actual cloud resources are provisioned.
Right, so it's evaluating before it even knows what you want to build.
Yes. And to configure the Cloud Foundry provider, you must supply it with the Cloud Foundry API endpoint URL. But that specific API URL only exists on SAP servers after the BTP environment instance is fully provisioned.
So it's literally impossible to provide it at initialization.
Exactly. Because that variable is unresolved at the moment you hit enter, the script fails immediately. You get an error stating the provider configuration is missing required arguments.
Which means the monolithic multi-provider run is architecturally impossible in this context.
100% impossible.
We cannot rely on a single state file. We must physically and logically split the Terraform configuration into a multi-step sequential setup.
Transitioning to separated sequential state boundaries is the only viable path here, and that requires a complete physical refactoring of your workspace directory structure.
Let us explore the architectural logic of that state split. Decoupling the BTP infrastructure layer from the Cloud Foundry operational layer actually provides a massive security and stability benefit.
Oh, absolutely. Blast radius isolation.
Right. If a junior developer pushes a bad commit that misconfigures a Cloud Foundry space role binding, that failure is contained.
It stays in the CF layer.
Exactly. It will not taint the core state file that governs your entire enterprise TTP global account structure, your subaccounts, or your overarching entitlements. We are respecting the mechanical dependency sequence while simultaneously building a more resilient, modular architecture.
Moving from theory to execution, you must physically restructure your workspace. You can't just create a new .tf file in the same folder.
It has to be a hard separation.
Yes. You must segregate the directories, because leaving legacy state files mixed together will corrupt the new multi-step flow. Let's walk through the exact CLI sequence, assuming you're staring at your terminal inside the current failed monolithic directory.
Okay, action item 1. I need to ensure a clean slate. I don't want any residual plans confusing the engine.
Right, so you execute rm.tf plan to destroy any cached binary plan files.
Just wipe them out completely.
Yeah, applying a stale plan after a directory restructure is a guaranteed way to cause a state mismatch.
Makes sense. Once the slate is clean, action item 2 is creating the physical boundary for our initial BTP build. I assume I just run mkdir BTP. Now we have an isolated folder.
Action item 3 is migration, and this is where I see engineers consistently destroy their own infrastructure tracking.
Oh, really? How so?
Well, we need to move all the existing BTP-focused Terraform files into this new directory. The command mv.tf BTP is pretty obvious, but you must explicitly move the hidden directory and the state file.
Let's look under the hood there. If I just move the .tf files and I forget the hidden files, what actually happens when I run my next command?
You trigger a catastrophic synchronization failure.
Ouch.
Yeah. The .terraform directory caches your downloaded provider binaries and your backend configurations. More importantly, the terraform.tf state file is the literal JSON database, mapping your declarative code to the physical reality on SAP servers.
So the state file is the actual brain of the operation.
Exactly. If you execute mv.tf BTP but leave the .tf state file in the root directory, your new BTP folder essentially has amnesia.
Because Terraform looks at the new directory, sees no state file, and assumes this is a brand new greenfield deployment.
Yes, and the next time you run Terraform apply in that new folder, Terraform will attempt to reach out to the SAP BTP API and recreate the subaccount from scratch.
But it already exists.
Right, so the SAP API will respond with a 409 conflict error because a subaccount with that name or ID already exists, and your pipeline will just crash.
So how do we avoid that?
You must execute mv.terraform BTP and mv.terraform.ts state BTP.
A critical save. You must migrate the amnesia prevention files. Okay, so our BTP configuration is fully corralled into its own directory. What is the structural move for the Cloud Foundry side?
Action item 4. Step back to the root level of your workspace and create a sibling directory. Execute mddir Cloud Foundry.
The workspace is now officially bifurcated. We have a BTP directory for layer 1 and a Cloud Foundry directory for layer 2.
Clean and separate.
This means we are now ready to explicitly configure the new Cloud Foundry provider within its newly isolated environment.
You execute cd Cloud Foundry to navigate into the empty directory. We are building from the ground up, but this time, our configuration will ingest the outputs of the BTP run as its foundational inputs.
Which introduces a pretty complex dependency management challenge. How do we pass the dynamically created API URL from the BTP state file over to the newly initialized CF state without hard-coding it?
because hard coding is terrible practice.
Right. Hard-coding a dynamic cloud endpoint completely defeats the purpose of infrastructure as code.
We bridge that gap through explicitly defined variable injection.
Mm.
Inside your Cloud Foundry directory, your first configuration step is creating a provider.tf file. You declare the Cloud Foundry provider block here.
And we need to ensure we are pulling from the correct registry source, not some deprecated community module.
Absolutely. You must specify the official HashiCorp registry source, which is Cloud Foundry Cloud Foundry.
Good to know.
Furthermore, version pinning is non-negotiable in enterprise environments. Currently, you should pin it to version 1.1.0.
Why is pinning so critical?
If you allow Terraform to float to the newest version automatically, a future breaking change in the provider's schema will suddenly fail your CI/CD pipelines.
Unpredictability is the enemy of CI/CD.
Exactly. So inside this provider block, we map the required API URL parameter to a variable, writing apurl_auth equals var.cfapul.
That instructs the provider to look for an external input. So our next file must define that variable structure.
You create variables.tf. Inside this file, you write your variable definition blocks for cfapul and orget. Both must be strictly typed as type in string.
But declaring the variables does not populate them with actual data.
No, it just creates the placeholders. For runtime data injection, we create a third file, terraform.tfafures.
Here is the manual bridge in our current pre-automated phase. How does an engineer physically move the data between these two decoupled directories?
You open a secondary terminal session, navigate into your BTP directory, and execute the Terraform output command.
Assuming you actually configured outputs in the first place.
Right, provided you configured your BTP resources to output their IDs upon completion, the terminal will render the generated Cloud Foundry API URL and the specific organization ID.
Okay, so they're on the screen.
You copy those string values, switch your focus back to the Cloud Foundry directory terminal, and paste them as key value pairs into your terraform.tvars file.
It is a manual handover for now, but it establishes the core architectural pattern we need. Directory A provisions the foundation and exports the endpoints.
And Directory B ingests those endpoints as input variables to authenticate its own provider.
Authentication brings up the next critical layer, credential management. Provider version 1.1.0 requires more than just the API URL to establish a connection.
It needs administrative authorization to actually build the spaces. It requires a username and a password.
And to be unequivocally clear from an architectural standpoint, we cannot put those credentials in the terraform.tvars file. I do not care if this is a temporary sandbox subaccount. If you commit plain text passwords to a Git repository, you are fundamentally violating enterprise security architecture.
It's a huge red flag.
Once a secret is in the commit history, it is compromised forever, even if you delete the file later.
Which is why we rely entirely on environment variables for sensitive authentication data. In our workflow, we utilize a .env file structure,
Right.
specifically a dev container .env file if you are utilizing VS Code remote containers, which isolates your development environment. You define standard export commands, export BTP user, export BTP password, export CF user, and export CF password.
But how does Terraform know to look for those specific shell variables? I mean, we didn't tell it to.
The Terraform engine is designed to inherit the shell environment it runs within. If the user and password arguments are absent from the provider.tf block, the Cloud Foundry provider is programmed to automatically fall back.
Oh, that's clever.
Yeah, it searches the host operating system's environment variables for specific keys, usually prefixed with CF_. This natively injects the credentials straight into the Terraform process running in memory.
Completely bypassing your physical code base on disk.
Exactly.
So the blast radius of a compromised code repository remains limited to the infrastructure design, not the administrative access keys. That is proper security posture.
It's the only way to do it.
Our Cloud Foundry provider is now configured, securely authenticated, and possesses the dynamic API URL it requires. The next logical phase is provisioning the actual operational resources. We have to map SAP's organizational hierarchy into declarative HCL code.
And the structural hierarchy on SAP BTP is incredibly rigid.
Right.
A Cloud Foundry space cannot exist in a vacuum. It must be provisioned inside an existing organization. Furthermore, human users or service accounts operating within that space require strictly defined role bindings.
Specifically, the space manager and space developer roles. Let's execute the space creation first. What does the resource block look like?
Inside your Cloud Foundry directory, you create a new file named main.tf. You begin by defining the core space resource block using the syntax resource Cloud Foundry space project space.
Okay, standard resource block.
Inside this block, the engine requires the parent context. We supply this by mapping the org parameter to the variable we passed over earlier, -ord.orgid.
The next parameter is naming the space. Architecturally, we want a dynamically computed name. If we allow engineers to hard code names like, I don't know, dev space 1, we will inevitably face naming collisions.
Oh, naming collisions are a nightmare. You get a completely fractured naming convention across the enterprise.
We need the code to enforce uniformity.
We enforce that using string interpolation. Instead of a static string, we assign the name parameter a combined variable string.
How does that look in HCL?
The syntax is named var.sage.projectname.
Got it.
If your terraform.tvars file defines the stage as prod and the project as inventory, the Terraform engine computes the string prod inventory during the plan phase.
This guarantees absolute uniformity across hundreds of micro-deployments.
Yes. The space resource is now defined. But an empty space without user access is just a stranded compute silo. We need to handle the role bindings.
Right. Who can actually use it?
We append a second resource block below the space, resource Cloud Foundry space role, space developer. This block expects 3 mandatory parameters: the target space ID, the role type, and the username being granted the access.
Okay, let's go through those.
The type parameter is a simple static string, in this case, space developer. The space parameter, however, is where we leverage Terraform's execution graph.
This is where implicit dependencies finally come back into play, but this time legally, because we are dealing with resources, not providers.
Exactly the distinction we needed earlier. You cannot hard-code the space ID because the space has not been generated by the SAP API yet.
Because it hasn't run.
Right. Instead, you reference the resource block sitting directly above it in the main.tfsci file. You map it as space Cloud Foundry space.project space.id.
By chaining that attribute, Terraform's DAG recognizes the relationship. It builds a directed edge from the role resource to the space resource.
Yep.
It mathematically proves that the role binding cannot be executed until the space resource reports a successful creation and returns its unique generated ID back to the state file.
The execution sequence is handled automatically. That solves the space ID. The final parameter is the username. This requires assigning an actual email address to the role.
Which we probably don't want to hard code either.
Right. We pass these as variables as well.
Yeah.
In your variables.taf, you define space developer email and space manager email.
Yeah.
But we must implement a critical execution step for security here.
Oh, this is vital.
Inside those variable definition blocks, you must append the parameter sensitive true.
Let us unpack the mechanism behind that flag. Why is sensitive true an absolute requirement for passing email addresses?
Because enterprise user emails are classified as personally identifiable information, or PII.
Right, privacy laws apply here.
By default, when Terraform executes a plan or an apply, it dumps the entire state of the resources it is processing directly to the standard output buffer in your terminal.
Which seems harmless if it's just on your laptop.
But if you configure role bindings without the sensitive flag in an enterprise pipeline, your console outputs, and much more dangerously, your centralized CI/CD pipeline logs will cache those email addresses in plain text.
Anyone with read access to the GitHub Actions or Jenkins log files, or even tools like Datadog or Splunk, can simply scrape the logs.
Yeah, they could map out your entire organizational directory structure.
Identifying exactly who holds administrative access to which production spaces. It is an immediate audit failure.
By enforcing sensitive true, you are instructing the Terraform engine's output formatter to intercept that specific variable.
So it still uses the email, right?
The engine still executes the JSON payload to the SAP API using the real email address, but it masks the actual string in any terminal output, plan file inspection, or log file, replacing it with the literal text-sensitive value.
It is a single line of configuration that separates a secure platform from a massive data leakage liability. So our Cloud Foundry configuration is entirely codified.
Ready to go.
We have the PIN provider, the injected variables, the space resource, the DAG mapped role bindings, and the PII masking. It is time to execute. Walk me through the systematic CLI sequence inside the Cloud Foundry directory.
The workflow begins with Terraform init. In your terminal, you will see the engine reach out to the HashiCorp registry.
Fetching the provider.
It downloads the Cloud Foundry provider, version 1.1.0 binary, places it in the hidden .terraform directory, and generates a .terraform.lock.hcl file to guarantee cryptographic consistency for future runs.
The stage is set. What follows initialization?
Execution discipline. You run Terraform FMT. This formats your HashiCorp configuration language to the canonical standard, aligning equal signs and correcting indentation.
Clean code is happy code.
Always. Next, you execute Terraform validate.
Let's pause on validate. For a listener who assumes validate just checks if the file is saved correctly, what is the underlying mechanism there? What is Terraform actually checking?
Terraform validate parses your code into an abstract syntax tree, or an AST.
Oh, so it's doing compiler level checks.
Exactly. It runs a lexer over your .tf files, breaking the code into tokens, and then builds a hierarchical tree structure to ensure grammatical correctness without ever touching the Cloud API.
So no network requests yet?
None. It verifies that your variable data types match, that you aren't referencing a resource block that doesn't exist, and that your implicit dependencies actually form a valid non-circular graph. If validate returns a green success message, you are structurally sound.
So the AST is verified. Now we need to see what the engine intends to do with it.
We enter the planning phase. However, in an enterprise workflow, you do not just run a naked Terraform plan. No, you execute Terraform plan out unit 4.1. This instructs the engine to calculate the delta between your code and the current cloud state, and then serialize that exact execution plan into a binary file named unit 4.1.
I want to push back on that. If I'm just running this locally, why add the friction of outputting to a binary file? Why not just read the plan on the screen and then type Terraform apply?
Because a cloud-level race condition.
Okay, explain that.
Imagine you run Terraform plan. You spend 60 seconds reading the output on your screen to ensure it looks correct. During those 60 seconds, another administrator manually alters a setting in the BTP cockpit.
Ah, state drift.
Right. If you then run a standard Terraform apply, Terraform throws away the plan you just read, calculates a brand new plan based on the altered state, and executes it immediately without giving you a chance to review it.
You essentially authorized a plan you never saw.
Exactly. By executing Terraform apply unit 4.1, you are feeding the engine the exact frozen binary snapshot.
So it's deterministic.
Yes. If the cloud state shifted during your review window, the engine will detect a mismatch between the binary file and the live state, and it will intentionally crash, protecting you from a race condition.
It provides cryptographic assurance that what you reviewed is exactly and only what gets applied.
Which is what you want in production.
Absolutely. When we review that plan output on the screen, we will note exactly 3 additions: the CF space, the space manager role, and the space developer role. And crucially, looking at the username fields, the terminal will print sensitive value, verifying our PII obfuscation is active.
The plan is verified. You execute Terraform apply unit 4.1. Because you provided a file, Terraform bypasses the manual yes confirmation prompt.
It just goes.
The engine initiates authenticated PLC request to the Cloud Foundry API, creates the space, binds the role collections, and returns an execution success message.
Let us translate that declarative code into physical reality. If you, the listener, open a web browser right now, log into the SAP BTP cockpit, navigate into your global account, and click into the subaccount we provisioned in Directory 1.
Yeah, trace the steps.
If you look at the left-hand navigation menu, click into Cloud Foundry Environment, and then select Spaces, you will see it. The newly created space, bearing the exact dynamic naming convention we codified via string interpolation, is active.
And the roles are there too.
Yes. If you click into that space and navigate to Members, you will see the Space Manager and Space Developer role collections correctly bound to the specific PII masked email addresses we provided.
We have forced infrastructure into existence through sequential multi-provider code execution.
It is a massive milestone. However, as an enterprise architect, I look at this and see an incomplete product.
Incomplete. We just built it.
We have successfully provisioned the infrastructure, yes, but provisioning is completely useless if the application developers do not know where their workspace is located.
Ah, that is the traditional infrastructure silo. A platform engineer builds it, closes their terminal, and assumes the job is done.
We must architect a handover. This is the paradigm shift where we start treating infrastructure as code, like actual software engineering.
Okay, I see where you're going.
The platform team's objective is not merely provisioning compute resources, it is enabling application development. An application developer should not be forced to log into the complex SAP BTP cockpit, navigate through a maze of global accounts, drill down into specific sub-accounts, and hunt through Cloud Foundry menus just to locate their assigned space.
No, that workflow generates immense friction. The developer's cognitive load should be entirely dedicated to writing Java or Node.js business logic, not decoding cloud control planes.
Exactly the problem. IAC must behave like a standard programming language. When a developer calls a function in Python, they expect it to return a usable value.
Right.
Our Terraform architecture must return the exact clickable URLs the developer needs to start coding immediately. We need to programmatically construct endpoints.
Terraform handles this behavior natively through output blocks. These act as our return values.
How do we set those up?
We will design our configuration to dynamically generate direct URLs to both the BTP subaccount overview and the deeply nested Cloud Foundry space, printing them directly to the terminal when the deployment concludes.
Let us break down the underlying logic of constructing an SAP BTP endpoint. A BTP URL is not a randomized hash. It is a very specific, concatenated sequence of technical UUIDs.
Right, it's predictable.
To build a valid subaccount URL, we require two components, the global account ID and the subaccount ID.
Which means our execution context must shift back to our first directory. You execute cd BTP in your terminal, returning to where the subaccount state file resides.
Back to the foundation.
Now, we already possess the subaccount ID because our code created that resource. However, we do not necessarily have the global account ID readily available as an output from a resource block.
Right. If we don't own the global account via Terraform because it pre-exists, our company already had it, how do we query its metadata?
We implement a data source block. This is a critical distinction in Terraform.
Data versus resource.
Yes. A resource block instructs Terraform to create, update, or delete cloud infrastructure. A data block, conversely, acts purely as a GET request. It allows Terraform to read information from the cloud provider without attempting to manage or alter the underlying object.
So it's safe to run anytime.
Completely safe.
Yeah.
In your main.tf file within the BTP directory, you append data BTP global account.
That block instructs the BTP provider to query the SAP API and retrieve the full JSON metadata payload regarding the global account that the current credentials are authenticated against.
We now possess all the necessary raw materials. The next step is constructing the output. You create a new file in the BTP directory named outputs.tf.
And what goes in there?
Inside, you declare an output definition output subaccount role. Within this block, we construct the final string by concatenating the static SAP cockpit URL prefix with our dynamically queried variables.
What does that string interpolation actually look like in HCL?
The syntax is structured as value. https://cockpit.btp.cloud.subaccount cache.global account data.btp global account.this.id subaccount.
btpsubaccount.project.id.
We are dynamically weaving the read-only global account ID and the managed subaccount ID into a static URL template. It is an incredibly elegant programmatic solution.
To manifest this output, we must perform a state refresh. Remaining in the BTT directory, you run Terraform FMT to normalize the code, followed by Terraform plan.
Framing the scenario for the listener, when you run the plan command this time, the output will look slightly different. Terraform is going to explicitly inform you that 0 resources will be created, 0 will be destroyed, and 0 will be modified.
That is correct, because our code additions were strictly a data read and an output definition. We have not altered the desired state of the physical infrastructure.
So the plan is basically empty.
Mostly. However, the plan will display a note indicating that changes to outputs have been detected. To commit that change, you run a standard Terraform apply.
And then what happens? The engine refreshes its state against the SAP API, computes the string concatenation, and prints the newly calculated, fully formed subaccount URL directly into your terminal standard output. You can literally hold the command key, click the link in your terminal, and your browser will launch directly to the subaccount overview page. Handover phase 1 is complete. We now need to execute the exact same programmatic construction for the Cloud Foundry space, which resides in the second directory. This requires passing the newly generated data across our established state boundary one final time.
Another manual handover.
Yes, you copy that minted subaccount URL from the terminal output, navigate back to the operational directory via cd.cloudfoundry, open the terraform.tavars file, and paste the string into a new input variable, which we will call var.subaccountURL.
We do this because the Cloud Foundry space URL essentially acts as an extension or a deeper path of the subaccount URL. It appends the specific organization ID and the space ID.
Correct. Inside the Cloud Foundry directory, you create a mirroring outputs.tf file. You define an output block named spacerel.
And the string construction here.
You construct the final string by taking the injected var.subaccountRel, appending the static path spaces, and then dynamically injecting the var.org alongside the Cloud Foundry space.project space.id, which is fetched directly from the local resource execution block.
And we execute the standard loop one last time.
Terraform FMT, Terraform validate, Terraform plan, and Terraform apply.
Again, 0 infrastructure modifications occur.
Right. But the terminal will now generate a deeply nested, highly complex URL string. When a developer command clicks that link, they entirely bypass the global account landing page, bypass the subaccount dashboard, bypass the organization tier, and land instantaneously inside their dedicated Cloud Foundry workspace.
This represents a massive reduction in developer friction. We have successfully provisioned a multi-provider infrastructure and programmatically generated the exact navigation vectors required for immediate productivity.
It's a huge win.
However, if we zoom out and look at the enterprise architecture as a whole, we are still facing a severe operational bottleneck.
The human execution bottleneck.
Yes, we have codified the entire process, but we are still manually executing CLI commands on our local laptops. We are still manually copying output strings from directory A and pasting them into directory B.
Which is fine for a sandbox, but not at scale.
If an enterprise supports 500 separate development teams, a platform engineering group cannot sit in a terminal running Terraform and copying variables all day for every single developer environment request. We must scale this. We need to operationalize a zero-touch self-service model.
This is where we elevate the architecture. We completely remove manual CLI execution from the equation by wrapping our modular Terraform workflow inside a centralized CI/CD pipeline.
How do we achieve that?
For this solution, we will design the architecture utilizing GitHub Actions, employing a methodology known as issue ops.
Let us unpack the concept of issue ops. But before we get into the pipeline execution, I have to throw a massive governance red flag on the play.
Let's hear it.
Automation is incredible, but creating SAP BTP subaccounts and allocating Cloud Foundry memory quotas consumes actual cloud credits. It costs real money.
It definitely does.
If we build a self-service pipeline where developers can simply request environments at will, how do we prevent a runaway script or just a massively overzealous development team from draining our entire SAP cloud budget in a single afternoon? We cannot implement zero-friction provisioning without stringent financial governance.
It is the single most critical failure point in platform engineering. If you automate without governance, you are automating your own bankruptcy.
Exactly. So what's the architectural solution?
The solution is that self-service does not equate to zero approval. We implement strict manual governance gating directly within the automated pipeline sequence.
Okay, walk me through that.
The workflow fundamentally changes. Step 1 is the developer request. The application developer never touches a Terraform file. They navigate to the platform team's repository and open a GitHub issue. But this is not a blank text box. It is enforced via a GitHub issue template.
They are essentially filling out a standardized digital intake form.
Precisely. The template prompts them to input exactly the parameters our Terraform scripts require. They type in the project name, for instance, inventory service. They are mandated to provide a valid corporate cost center, such as CC 98765.
So billing is tied immediately.
Yes. They select a geographic deployment region from a locked drop-down menu, perhaps US 10. They define the environment stage, like dev or ca. Finally, they input the space manager's email address.
They fill out the form and hit submit. Now, does the GitHub action immediately spin up a runner and execute the Terraform apply?
Absolutely not. This is where the governance gate halts the process. The submission of the issue triggers the GitHub action webhook, but the pipeline workflow is explicitly configured with an environment protection rule.
So it pauses.
The pipeline initiates, but immediately enters a waiting state. It pauses execution entirely.
This is the platform approval phase.
Yes. A platform engineer, or specifically a manager who holds the budget authority for that cost center, receives an automated notification. They review the GitHub issue payload. They verify the cost center against the corporate ledger.
And if it's unauthorized?
If the request violates policy, they reject it. Pipeline dies. If everything aligns, they click a physical approval button within the GitHub UI. That manual click is the key that unlocks the pipeline.
So we have achieved a perfect synthesis of strict financial governance paired with automated, rapid execution. Once that manager clicks approve, what is the pipeline actually doing under the hood? Walk me through the mechanics of the runner.
The GitHub action is governed by a YAML workflow file. The YAML dictates the entire lifecycle. First, it spins up an ephemeral Ubuntu runner, a temporary virtual machine that exists solely for this deployment.
Okay.
The first task the runner executes is parsing. It uses shell utilities, often a combination of grep, awk, or JQ, to parse the raw markdown text of the GitHub issue body and extract the submitted variables.
It is dynamically scraping the issue to generate the terraform.tvars files that we were previously building by hand.
It injects those variables directly into the workspace. Crucially, it takes the extracted cost center variable and maps it to a resource tag within the BTP subaccount configuration, guaranteeing that all cloud consumption billing is perfectly tracked back to the requesting department.
That solves the finance problem.
Then, the YAML script handles the multi-directory sequence. It changes directory into BTP, executes Terraform init, FMT, validate, and apply, auto-approve.
Wait, how is it authenticating to the SAP API without our devcontainer.env file? We aren't passing that to GitHub, are we?
Oh no, that's handled through GitHub secrets. The pipeline is configured to pull the highly sensitive administrative credentials securely from the repository's encrypted secrets vault, injecting them into the ephemeral runner's environment variables at runtime. Once the BTP layer finishes applying, the YAML script utilizes Terraform output JSON to extract the API URL and org ID, dynamically writes them into the CF directory's terraform.tvars file, changes directory, and executes the exact same automated deployment loop for the Cloud Foundry layer.
And it does all this without a human.
All of this occurs in minutes without a single human keystroke.
The machine is performing the directory hopping and data bridging flawlessly. And here is the most powerful architectural feature of this entire setup, the return loop.
The closing of the communication circuit.
Exactly. Once the final Cloud Foundry apply is successful, the pipeline must deliver the results. The YAML workflow is programmed to read the final outputs.tf string values, the subaccount URL, and the space URL.
Right.
It takes those strings, formats them into a clean markdown table, and utilizes the GitHub REST API to automatically post that table as a comment back onto the original GitHub issue that the developer opened.
Which is just an incredible developer experience.
The developer, who has been waiting at their desk, receives a push notification on their phone or an email stating, "Your environment has been provisioned." They open the GitHub issue, and sitting right there in the comment thread are the exact clickable URLs they need.
Boom, ready to code.
They click the link and drop straight into their pristine Cloud Foundry workspace. The entire infrastructure lifecycle request, approval, provisioning, and handover is handled entirely within the issue tracker. The application developer never saw a single line of HCL, they never installed the Terraform CLI, and they never once had to look at the SAP BTP control plane.
That is the ultimate platform engineering handover. We have transitioned from a tangled, monolithic provider limitation, restructured our state files into a sequential architecture, secured our PII and credentials, generated dynamic endpoints via data sources, and fully automated the delivery mechanism through IssueOps.
It is a massive technical journey, and it demonstrates a masterclass in treating infrastructure not merely as configuration files, but as a robust, scalable internal software product. We have unpacked the mechanisms of the Terraform initialization phase, the graph theory behind implicit dependencies, the severe dangers of mismanaging .tf state files, and the intricacies of YAML-driven CI/CD automation.
The architecture is now scalable, secure, and highly developer-friendly.
And that leads me to a final forward-looking architectural concept I want to leave you with, something that builds directly on the foundation of this CI/CD handover.
Oh, look into the future.
Yeah. If a GitHub action can parse a Terraform output and utilize an API to paste it into an issue comment, what happens when you elevate that automation even further?
I like where this is going.
What happens when you pipe that dynamic Terraform output directly into an internal developer portal, an IDP, like Spotify's Backstage?
That is exactly where the cutting edge of the industry is heading right now.
Imagine an architecture where the YAML runner provisions the BTP space, generates the URLs, and instead of just commenting on an issue, it makes a POST request to a centralized Backstage catalog.
The automation just keeps building.
Instantly, a fully configured browser-based IDE environment, complete with valid Cloud Foundry routing and preloaded boilerplate code, is generated and waiting for the developer on a unified dashboard before they even ask for it. The infrastructure isn't just code anymore, it is a living, self-documenting service catalog. That is the next frontier of platform engineering.
It's an exciting time to be building on BTP.
It really is, something to mull over as you build out your own enterprise capabilities. Thank you for joining us in the architecture room today for this deep dive. We will see you next time.